So yeah, so we've discussed the three examples. That would be great. And make a poster of it. And it says submit a photograph of your poster, and that's what you're going to submit when you put it into Turnitin, so that you'll have your essay basically and the photograph. And the poster, as it says, is just one of your examples, because there's no way you'll be able to fit all of them. Just make sure that you've ticked all the boxes as you go along. So demonstrate subject, pedagogical and curriculum knowledge and its impact on pupil progress. The same obviously as what you would be showing in the written bit. And and then just be clear about, exactly all these bits. So a bit of theory, and you could just put them in little boxes like this, the theory, just as we discussed, what you noticed, theory relating to this, what you decided to do, and how it made them progress. Yeah, so I mean that just talks you through what you're supposed to be doing. And go on, yeah.
Just a quick one. It says 3,000 words percentage mark. Is that 3,000 words on the writing and then the poster on top of it, or is it 2,000 the writing and 1,000 for the poster?
It is kind of an overall, I think we discussed. Yeah, and let me just I think it's total, but I'm not going to penalise you. I'm not going to penalise you either way. I mean, if you write 3,000 words and then your poster obviously has additional wordage, as it will, that's fine.
Right.
If you find it difficult to write 3,000 words, we'd rather just write 2,000 and have 1,000 in the poster. That's fine. I don't think it will matter either way. I think we could argue it either way, basically.
Yeah, I just didn't want to go over the wordage and mark myself down, as it were.
Yeah. I always think I'm never going to hit 3,000 words, and then I'm always, desperately trying to cut stuff.
Yeah.
But yeah, I think that'll be fine, because the poster is kind of, in addition, I'm going to be marking, I'm just going to read this again, actually. Select 3 different examples of evidence you've uploaded to your e-portfolio. To demonstrate each example needs to be drawn from. Now, actually, I'm just rereading this. And it's basically saying, sorry, I don't know why I'm talking about an essay or anything. There isn't one, is there? Effectively, you're just taking 3 examples that, of course, are already uploaded to your e-portfolio that demonstrate this. I don't think you're actually writing about them, are you? You're just choosing 3 examples and then selecting one that you're drawing out.
Yeah.
Yeah. So you submit 3 selected excerpts from the e-portfolio, and I think that basically, as part of that, there's the expectation that the things that you've uploaded to PebblePad, or your e-portfolio basically, are quite, like the best you've ever written them, in terms of they go through each of these things.
Yeah.
So you still need to do what we've discussed, but it's not in an essay format. It's just in 3 little excerpts that should be as part of your e-portfolio. So I don't know if you normally, how you normally write those. Do you normally do them as with sort of the sort of critical appraisal that is expected of the assignment, or?
It's usually I'll plan it from a lesson, then I'll in the little section B or C, where it says review on the lesson plan.
Yeah.
I'll critique it in there.
Yeah.
Like what went well, what didn't, what I'm going to do for the next lesson.
Yeah. I think the difference between these two things, that one obviously is just a reflection more than
Yeah.
critical. It's not, obviously you don't normally get theory and research, do you, when you're doing your lesson plans and stuff? You're more looking at just how it
No.
impacted on the students. So that's the key difference, isn't it? Demonstrate depth and systematic understanding key ideas in special subject. Analyze the particular impact of system knowledge. Critically engage with and analyze the relationship theory concept. Just so you're basically just sending me 3 different examples of evidence that demonstrate your personal developing subject knowledge and must demonstrate how it has impacted on people's behaviour. I am going to clarify because it's not clear, really, is it? It seems to be suggesting that only one of your examples do you have to really draw out all of the theory and do all of that, which makes sense. That's more fair based on what previously happened in terms of the thing. But then the question is, then why on earth do you need to submit 3? That's just ticking.
Yeah, that's what's sort of been blowing my mind. It's like reading, obviously reading the assignment brief. It's like reading stereo instructions.
Yeah, and I thought I understood, and I thought, and then you think, because I thought you were kind of going to be just drawing out, doing this like little potted thing for each one. Notice a problem, get some theory, do something, sort evaluate how successful it was in terms of people progressing. For each of those 3 things, that's what I was thinking. Basically, very safe.
Yeah, that was my thoughts.
Yeah, and then you choose one of those and make it pretty, basically, as a poster.
Yeah, so I've done this bit of research into these 3 subjects. I'm going to display this to my peers.
Yeah.
In order to advance their professional progress.
Yeah, so that was what I thought. Now that I'm rereading it, I'm then thinking, do these 3 need to be that intense, or could they just be like the examples that you normally put up in Pebblepad, and then one is expanded on the poster? Obviously, your safest bet is the first option, because that's definitely not wrong. Because if you've done research for all of them, and they're all brilliant, then that's all fine, isn't it? That's definitely safest. But I will email Liz and see if I can gain clarification on that.
Excellent.
Yeah. Right. Let's move on a bit. Yes, and all the details of your giant poster. With the portrait as well. I think that's so that they can fit as many on the walls as possible. Because they're planning apparently. I think they're going to put them up at Warwick on your final meetup.
I was actually not. Yeah, because they said we've got to bring them in on our next study week.
Yeah.
Then I've seen a photo. So I was like, oh.
Yeah. So the photo is uploaded to Turnitin for me, so that
and then the poster's brought with me.
Yeah, and the poster you brought with you, I guess, I give to, I don't know, Liz or someone in the house, or whoever's going to collect them all up, and then they're going to stick them up on the walls at Warwick for when you come back the next ISW. So yeah, and also because previously where we'd done things like this, and I'd just been given stuff, there was then no record on Turnitin, which officially, for Ofsted, they then can't see the actual poster. So that's why there's the photo thing, because what was happening was people were submitting things direct to me, and then I was having to then take pictures of stuff and send them back, submit themselves. So that's why that's sort of doubling it up. Right, but
that's not a problem.
I'll confirm about the content. But either way, you can definitely get started. Do one of them at least. If not, develop the others. Before I get back to you.
Yeah, I mean, I'm planning on starting them next Thursday because my laptop's been touched up while I'm at my second placement. I'm going in for a parents' evening on Wednesday, so I'll be able to get it fixed then.
Okay. Have the school given you a laptop, have they? Or is that your own?
Yeah, I use my skills laptop because my personal one, something's wrong with it. The
So,
power, the power patch won't charge it up.
oh, that's annoying. Yeah.
Yeah, so I'm using the skills one, which is a bit better than mine, to be honest.
Hmm. Yes, I'm stuck in in between place where my laptop keeps failing. I was delighted that it's actually booted up today because Wednesday it didn't boot at all.
Oh, crap.
And all my stuff is on it. And I have been given one by the university, but I haven't yet put all the stuff on it, which is why I keep using my old one. Oh. So hopefully at the ISW, I'll have switched everything over to the new one before mine dies.
Yeah.
But yes, anyway, we've only got 2 more webinars, and I've done all the cohort 4s, so my laptop doesn't have to survive much longer. It's all right. So today I think we'll probably whip through the first one because I have this first bit about theories of learning and approaches because we've talked about it a lot and I should probably have brought it forward in the agenda really. And then I've put quite a lot of maths in today. Proof, binomial expansion and sequences and theories. So that's all AS level maths. But, sort of normally they do middle of the year of the first sixth form year. So yeah, theories of learning we've I think probably talked about before, but some of these obviously like Lave and Dewey, well and Piaget will all be very useful people for your depending on what you did for each of your excerpts. Behaviorism very much was the traditional way of doing things and was how we basically got robots that we all are for a lot of our repetitive things that we don't even realise that we don't have deep understanding for. And there's been a definite move towards constructivism, but not as much as I expected when I got into teaching. But we're definitely always aiming now for greater understanding. It was very much a procedural thing that people used to do before, so instrumental. We tried to get more of a relational, so there are at least some connections now. Functional, well, it depends what you're trying to teach, but yes, this is the thing. Is there a conflict, I put, between the level of understanding that students and teachers want or need? And often I find that I'm fighting against, so although I'm trying to get them to have a deep understanding, they obviously aren't bothered and they're happy doing their procedure. And actually sometimes when you then introduce the greater depth of understanding, then they've suddenly got confused by something that they really understood before. Absolutely fine. And you have to sort of go, okay, forget everything I've said, just keep doing what you're doing. And you feel awful doing that, but then you're like, well, time is short. It's tricky, isn't it?
Yeah.
And definitely just depends on the students, doesn't it? I don't know if you notice particularly in a gender way. I mean, but personally, as a girl, I just wanted you to tell me a rule. I really wasn't bothered to understand why, but I loved getting things right. So, I just wanted to, here you go, do this. I do it 100 times. I get it. It's fine. It's lovely. Don't really care why. Obviously, that as I got further into math, I needed to understand why. But I definitely find with teaching boys, their understanding of doing is tied into their understanding of why.
Yeah, definitely.
Yeah, so they don't like to just follow a rule without knowing why they do it. I'm just thinking about my children actually, realising that that's so true with my son, where he's going, why do I have to do this? Why can't I jump off the sofa? It's like this endless sort of understanding. He won't just do what I tell him. He really has to understand why. It's only when he really has hurt himself in the head, and he actually still doesn't even get it. So yeah, so we have to appreciate that how we like to learn and how students like to learn is often very different as well. So bringing together Vygotsky's and Piaget's 2 theories, we get social constructivism, which is basically just how hopefully we teach more now, in that the students are collaborating together and discussing things, and the teacher is coming in and scaffolding. That is the ideal teaching scenario. You know, whether that happens all the time is unlikely. But Brunner is a good one for lots of maths. Joe Bowler is, I don't know if Jan Brunner is still alive. I think not. But Joe Bowler, I think Barbara Jaworski. So these three, in terms of constructivism and maths, these three are good for getting learning theories to do with problem-based learning, active learning, inquiry learning. So those are quite good ones for your, say, so yeah, so we've got some references here that might be quite useful. Right, let's get, approach to teaching as well, I think. In terms of what you think, and what I was saying about how it would be nice if everything was sort of socially, well, that's my opinion, isn't it? A lot of people just to sound the pastor and Paul. What do you notice within your school?
Well, being an all boys, I find that the younger ones just want to learn by practicing things.
Yeah.
And as they get older, they actually want to investigate and discover things for themselves.
Yeah.
So it's quite strange. It's like, a lot of the times I'll give them a set of problems that are differentiated, which they can self-differentiate with.
Mm-hmm.
And some of the less able will try and jump straight to the more difficult ones. They might spend the whole lesson just to get one question right. I see they understand it more because they've played with it. And others will just work their way through practicing the process until suddenly they get the light switch, and then they can jump to the problem-solving exercises or the challenge.
That's good that they seem to recognise in themselves their different needs and approaches, actually.
I mean, sometimes you do have to go around and say, right, why don't you try this one before you try this one?
Yeah.
So a bit of guidance for them.
Yeah.
I'm trying to get away from the old military practice to explain, demonstrate, imitate, practice.
Yeah.
Just because I think it's very prescriptive and
it's very
outmoded.
Yeah. Yeah, absolutely.
I like, with my seating plans, I've got kids of a similar level sat sort of in small groups around the classroom.
Right.
So that way, if they are working on a problem, they can help each other by using the 3 Bs before me.
Yeah.
So
and did you
get stuck in a problem there?
Do they know that they are sat in similar levels?
No, they don't.
Okay, that's good.
They think that I've just put them in a regular seating plan, but once we've done the assessments, they've started to see.
Okay.
Or I don't know if they've noticed it like consciously or just subconsciously.
Yeah.
They've sat around people who are similar levels.
Mm-hmm.
But we do get the more able helping out the less able.
Yeah.
And the less able asking the more able advice for advice as well.
Yeah.
And sometimes I find it's those that are less able mathematically are finding the easier ways, whereas those that are more able are overthinking it.
Yeah. Yeah, absolutely. Yeah. Well, that's really good that you've got that.
I'm very much.
I was going to say, it's good that you've got that environment within your class that they feel they can move around and talk to each other and help each other. That's great.
Yeah, I mean, with my year 8s, they're top set. They're brilliant. I've got one lad who's already got a 9B in term 1. So I really have to push him without, like, trying to put too much pressure on him.
Yeah.
Because, bless him, he was in tears and had to take 5 minutes out of the lesson because he made a silly mistake on his test that cost him a mark.
Yeah. Perfectionism is the biggest battle, isn't it? You know, and the problem is that whatever you say doesn't make them feel better. They've just got to learn their own ways of coping skills for that. Because no matter how many times you tell them it doesn't matter, it's like the end of the world for them.
I keep re-emphasizing that end is just an effort never dies and fail is first attempt in learning.
I know, absolutely.
Cheap and cheap the acronyms, but it works.
Yeah. What was end? What did you say end was?
Effort never dies.
Effort never dies. Okay. Good. Anyway, let's. So there we go. This is what was in 1982. This is the Cockcroft report. They were saying maths teaching should include all of those: explanation, questioning, discussion between teachers and students, practical work, consolidation, practical practice, problem solving, application math, and investigational work. Well, having grown up then, I can say that we definitely didn't have that. It just sat there. We just definitely sat there. Whereas, these are all different constructivist approaches: active learning, inquiry learning, problem-based learning, collaborative working, all slightly different. Sorry, set the telephone so that it doesn't pick up, and now it makes a weird noise. All slightly different. I think I probably tend to do more collaborative work in it, mostly out of those four. When it started, and this was we're talking only 15 years ago, and people suddenly were like, oh, hang on, we're not reaching everyone, they're just sitting there, we need to sort of do more active learning. That was definitely the word that sort of came in, and we did a lot of active learning, and that was the things like, the matching cards and getting up and doing things, that was the active learning. There was a lot of that. I think people thought that, oh look, we're not just sitting there talking now there's some active learning, but it wasn't truly necessarily constructivist. The kids actually were just having a load of fun. It was like the equivalent of wheeling in a video player. They were just like, yeah, great, we can relax, we don't actually have to do anything. Whereas, inquiry learning is very much kind of a throw them in the deep end, to get them to explore themselves, and just to going around scaffolding where necessary. And those probably are more like problem-based learning, where problem-based learning is a bit more structured. I think you give them the problem, whereas inquiry, they're sort of having to figure out what the problem is. And collaborative working is just good. Yeah.
Problem-based learning, is that sort of like the Japanese method, where they give them a problem at the start of the lesson?
I would say
let them try and work it out, then scaffold it through it. Yeah,
exactly. And then you get them to come up and explain their solution, and then people question them and that sort of thing. Exactly. And in fact, I think, that might be what I put in the next thing, using ILT. That was another thing that we did, but here we go. Yeah, exactly. So this is still a typical US lesson. The teacher reviews the concept of perimeter. Teacher explains how to find the area of a rectangle. Pupils do the practice. Then they explain how to find the area of a triangle. Pupils do the practice, and pupils work individually. We definitely do that as well in the UK.
Yeah.
But I think the idea hopefully now is that might be one small segment of a lesson now, rather than the whole thing. But you never know. Whereas, yeah, exactly. In the Japanese lesson, the teacher will present the complex problem. They will try and solve them, and they spend quite a lot of time doing that. And then they present it back to the class, and the class pick holes in it, and teacher will add to it, and then at the end they can have some time, working on practice problems. But you can see that obviously in the US lesson they're just going to be doing repetitive things. They don't even
individual
need
work,
to,
just
yeah,
practice.
yeah, they don't even need to really engage their brains necessarily, do they? They go, here's a formula, I'll just apply it. Whereas here, this is a much better way to do things. And in fact, I'm going to do we've got a joint session on the Monday afternoon at the ISW. So you'll be joining cohort 4.
Yeah.
And I'm gonna do about how to do this problem-based learning a bit more, how to set up sessions and stuff.
Excellent.
I thought that was something for everyone really, and this is my preferred way to work. Although not truly work. I observed one of the other teachers at the university doing it the other day, truly doing it, and she has done it her whole life and has only ever done that. She has never reverted back, because I definitely do a mixture of, okay, we've done that, great, now do some practice, and she doesn't do that at all. She very much just does it all from this. I mean, but we were all exhausted by the end of the lesson. I think that's the difference, isn't it? It really takes it out of you, having to work your brain that hard. The students would be knackered, but
yeah, I've done that sort of Japanese style lessons with end of topic problem solving.
Yeah.
I call them logic puzzles and riddles, but it's just mathematical problems I've put into a sort of fun way. And they don't realise they're actually doing quite a lot of work.
Exactly. And the thing is also that although you can seemingly give them totally random problems that have nothing to do with curriculum, ultimately they end up having to do numeracy and algebra, and just fiddling around with jigsaws can be enough to get their brain working and making connections in the right sort of way that it helps. So yeah, excellent. And there's some more, this is about different things. These guys here, they're very biased the other way. They in fact are, I mean, you have to, as an example, Michael Gove quoted these guys as his reason why everyone should just sit down and be told what to do. So this is like the opposite of all of this. They're really like, oh, constructivism doesn't work, all of this is rubbish. But that's because they were saying why minimal guidance doesn't work. It was all about, I think the whole crux of their thing is that ultimately it's about how good the teacher is at scaffolding. So, it's very weird, but anyway, it's good to include other sides. Right, let's talk about proof. So in GCSE, the sort of proof that students are required to do is mainly geometrical. They've got to apply angle facts and use their knowledge of Pythagoras and stuff in order to be able to do things to do with triangles and prove things to do with the circle theorems and that sort of thing. And then they have just a little bits where they have an identity and they have to show that one side equals the other side, show their equivalence. That's true. But it does say, this is the actual curriculum, it says, use algebra to support and construct arguments and proofs. So it's looking for a bit more rigour than GCSE used to have. So yes, the circle theorems, typically you're given these sort of questions, you're asked to do it, but the proof bit comes from writing down the associated theorem that goes with it, and that has always been expected, that they can't just write the angle, they have to justify why that is. Now at AS level, it goes a bit further, and we have much more rigorous deduction required. And what I'm not sure is whether they are going to bring, I wonder if that's available yet. Yes. Oh no, we're not there yet, are we? 2017. So we'll wonder whether they're going to try and go on.
It's third paragraph. Q to P means P is necessary for B. Is that a typo?
Oh yes, sorry. It is a typo, yeah.
So I just reading through it and it just
I thought I corrected that last time when I did this. Obviously completely forgot again. Yes, that is a typo. In fact, I'm doing that now.
okay.
Yes, because originally I'd written them all in A's and B's, and then for some reason changed that. Don't know why. But anyway, yes, so it could be that they started to bring in this sort of thing into GCSE, but I don't know. The sort of idea of generalising using algebra. So at AS level, there's sort of an expectation of knowledge with the students. They don't have it at all, really. Some of them do, definitely the people who sort of want to do further maths and stuff kind of get this notion that I sort of say, look, I need to talk about an even number in algebra. What could that be? And sort of like, I don't know what it is now. Well, let's think about the fact that every even number is a multiple of 2, so to get an even number, you have to do 2 times some number n. So, you know, if you're talking about even numbers, we can say 2n, and then an odd number can be either way. So you can either say 2n plus 1 or 2n minus 1 equally is an odd number. So at the moment, that's the thing, it's only at AS, but we will see whether those are the sort of very general things that come in. But yes, this, I couldn't get quite the right arrow, but really, so P implies Q means, yes, if P is Q, then Q is true. So the other way round means that, yes, P is necessary for Q. Q implies P, I mean, I don't tend to say sufficient and necessary. I know a lot of people do, but they don't generally use that terminology, or they don't necessarily use that terminology. I think they, you know, in terms of you're doing a proof, it's totally up to you how you like to say things. And I tend to write everything in shorthand and use the arrows. So definitely I think at GCSE the words sort of sufficient and necessary are, I don't know, a bit more complicated for them. But either way, when it comes down to the actual propositions, so here we have y cubed is greater than 1 is p, and y is greater than 1 is q. What can you say is any relationship between p and q?
Let's have a look. Q is going to be P cubed. No. I'm not 100% sure.
So basically in terms of the whether one can imply the other. So if P is true, is Q always true? Yeah. So yeah, so if generally to work these things out, we just suggest to the students that they try some numbers in it and get a feel for it. If this is greater than 1, so let's say it's 8, oh great, that would be 2 cubed, and 2 is greater than 1, so that works. However, if it was 2, I know, root 2 is still bigger than 1, no, that's fine. Oh no, cube root of 2? Oh, that's not calculated. What is the cube root of 2? Have you got a calculator there?
Cube root of 2 is 1.2599.
Oh good, so that's still bigger than 1 too. And what's the cube root of 1.1?
1.0322801115.
Okay, so yeah, because anything that must have a 1 and then 1 is going to be bigger than 1, isn't it? Right, so it seems to suggest that P does imply Q, if P is true, then Q is true. And equally, so if we've got this 2, so again 1.1 cubed, yeah, I think they imply each other, don't they? If Q is true, then that's going to be true as well. Yeah, so in this case, we get both ways. P is necessary and sufficient. So P is true if and only if Q is true. But that's not always the case. But they love to give these sort of things in AS, and they get, the students have to decide whether, they have to be true or whatever. So here's a few. I won't get you to do this first one because it's nice and simple. But if you're ever asked to prove an identity, and that's definitely something they could be expected to do at GCSE, then what they tend to do is sort of just do both sides until they equal each other, which is fine. Traditionally, I prefer to say left-hand side and do this side, and then I do another bit where I say right-hand side and I do the other side, and then I say left-hand side equals right-hand side, therefore it's the identity. But it doesn't matter if they go down doing it. It's just a little unsafe sometimes because they end up then forgetting that they were supposed to be looking at this side and that side, and they start solving it like an equation and wonder why they've got 0 because it all disappears. So I think it is safe to just split it into left-hand side and right-hand side. So the sum of any 3 consecutive even numbers is always a multiple of 6. Can you try to write down a proof of that using basically algebra? Have you done this sort of thing before at all?
I've seen it sort of before. I think I've got it.
Okay.
No, I don't.
Okay.
And all I did was take n as middle number, n plus 1 is the one below, n take 1, n, and n plus 1. Simplify it down, it comes to 3n.
Yeah. So that would be fine if it were just consecutive numbers, but here it's consecutive even numbers. So the same
even numbers.
Yeah, same thought process, but obviously you're just going to have it doubled because how you're going to get your 6n basically. But you're right. So that is exactly it. So it will just be 2n.
Yeah, so I've got to use 2n.
2n plus 2.
Yeah, which comes out as 6n at the end.
Yeah, I think you should get 6n plus 6. And so yes, I think you get 2n plus 2n plus 2 plus 2n plus 4. So you get 6n plus 6. And to show clearly that it's a multiple of 6, we should take the 6 out to show that it's 6 times something.
Yeah. See, what I did there, where you've done 2n plus 2n plus 2 plus 2n plus 4,
yeah.
Instead of having the 2n plus 4, I had 2n take 2.
Yeah.
So it had
6n.
My central number is just 2n.
Right. Yeah, so that's actually fine too. Yeah, so you just had 6n. Forget what I said.
Yeah, because it comes out 6n. Yeah.
Yeah.
Rather than 6n.
Absolutely. Sorry, I misunderstood what you're saying. Yeah, absolutely right. Good. Can you do, if you multiply 2 odd numbers, get an odd number?
Right, I should get 2 open brackets, n squared plus 2n plus 1 close bracket.
Say it again.
Doesn't look 2 open bracket, n squared plus 2n plus 1 close bracket.
Yeah, you should have. So
Double check my math.
odd numbers. So 2n plus 1 is an odd number. So
Yep.
what you, and then you can have either 2n plus 1 again, or you can have another odd number. I'll do 2n minus 1.
Yeah, I just put 2n plus 1 times 2n plus 1.
Yeah,
so in the quadratic, 4n squared plus 4n plus 2.
That's fine. No, but it's not plus 2. That's the key thing. It is just plus 1.
Ah, plus 1. That's where I went.
Yeah.
Mistake. That's my mistake, sorry.
Yeah, so then then you can take out,
fine.
you can basically take out that must be an even number at the front. Because you've got 2 even numbers in there. But when you add on a 1, it makes it an odd number. But this sort of thinking is where you need the students to be getting to, basically, at the top of GCSE and then into AS. And it's not something we do very much. This is the bit of maths that a lot of people really hate. This generalising just sort of like seems completely weird. And this is what my whole university degree was like. This is kind of the starting point for it, and then some. Nice way is when it's actually not true and you can just find a counterexample. So for example, n is an odd integer implies that 2n is an even integer. You just need to find a counterexample. So that is always true. So I don't know why that is. Oh, sorry, this bit goes with this bit before we get to this bit.
Yeah.
So I was talking about converse first. So converse is saying that although that's true that way, it's not true the other way. So if n is an odd integer, it's always even. But just because it's even doesn't mean that n is odd, it can be even as well. But yes, for this one, if you want to show for all integers n greater than or equal to 1 that is a prime number, to show it's false, you just have to pick a number. Sometimes it takes quite a long time, and the students think, "Oh, okay, I better have to prove it then." You know, maybe it is true, but I'm sure there's. It might be actually really simple. I'm not sure, is it? Oh, it works for quite a long time actually. Probably something like 11 that it stops working. So finding counterexamples. Well, can you figure out what the counterexample is for that? Oh, I think 6. I think it might be 6. I think that might give us 55.
Yeah, 11 works. It comes out as a 155, which is 5 by 31.
Yeah.
Sum of the product of 2 prime.
Cool. There's lots of methods of proof as well. So at AS level, they just are expected to use deduction, which basically, come up with some algebra and prove it logically, come up with a counterexample, use exhaustion, so that's where you literally just write down all the possibilities. And then in A2, they have to know contradiction as well, which is a bit trickier. And in further math, there's proof by induction, which is even trickier and possibly not strictly. So a common one that we do proof by contradiction is proving that root 2 is irrational. So what we're aiming for is to say something that we think is true and then prove that it can't possibly be true. So we assume that root 2 is rational. Now what that means, if we have a rational number, we can write it as a fraction. So if root 2 is rational, we can write it in the form p over q. They can't both be even because otherwise we could cancel by 2. So we know that both of those must be, at least one of them must be an odd number. So what I'm then going to do is root 2 equals p over q. I'm going to square each of them and then just multiply up. So I've got that 2q squared equals p squared. Now, because of that, that means that p must be even because I can write it in the form 2 times something. Then that means that p is the even number. So let's say that p is an even number and we'll call it 2k. Just going back to our sort of algebra of naming even numbers. Okay, so that's great. I've now write p in terms of k. Fine. However, if I can write p as 2k, then that suggests that my p squared is now 4k squared. And if I divide through by 2, then I can write q as 2k squared. So that then suggests that q is 2 times something. So q is even. But we very distinctly said we can't have them both even, because otherwise they would cancel and thus it would just disappear. So there's a contradiction and root 2 is irrational. It seems like a bit of a weird swizz, really. Let's pretend something. Oh, that's not possible. But it's done in a lot of things for maths as a way of sort of coming up with a proof. So that's proof by contradiction. Proof by exhaustion, you would literally just write these down. So there's no 1 or 2 digit perfect square ends in 2, 3, 7 or 8. And so basically the students would just write them all down. So their first thing would be to realise what a perfect square is, and then they just write down what 1, 4, 9, what we got, 1, 4, 9, oh, I've just, sorry, I guess that's 16, 25, 26, 9, 9 squared is 1, and that's all of them. So as you can see, none of them end in 2, 3, 7 or 8. So that's all you have to do to prove that first bit. And then what do you reckon the generalization is? Yeah. What do you think? How could you generalize this result? What has made this specific?
It's given you the result, you need 1 or 2 digits.
Yeah.
And you've given the end result, so it's 2, 3, 7, 8. So we know it's not going to be divisible by 2. In fact, no, scratch that.
Yeah, no, it's more about just the number that it ends in.
Oh, I see. It's 149656941.
And then the next one in, the next one in fact is 100. And then 121.
121, 144.
And then must be 169. Yeah. So they repeat.
And it keeps going up 400.
Yeah. So the generalization is no, you can just scrub that bit out basically. No perfect square ends in those digits, because of the fact that it always ends in the same ones round again, because of the way that each number, because the final number of these digits, the final digit of these numbers are always affected by the unit of the previous number, aren't they? So, if you square 3 or you square 13, the final digit is because of squaring that last bit.
Have that 9.
Yeah. So the proof's quite nice because it brings up little things that you really, well, didn't necessarily care about before, but, you know, didn't know either. But the students do find it very tricky, unfortunately. I've put this on here. It doesn't really work watching it through here, but it was just one of Marcus de Soto's proofs. He has done loads of proofs really well. If you Google sort of any of his, you know, history of maths things that he's done, then there are lots of nice proofs. I think have I shown you the one before that's got him and Alan Davies, and he was explaining how there are infinitely many prime numbers. I think that might actually be the same proof, but it's just done differently. So that's quite a nice one. So,
yeah, I think so. I can't really remember.
No, but anyway, if you ever want to show the students, like, a good way to start proof lessons is a nice way. It's difficult. You can either just leave them to it and see what they can do, see if they come up with proofs. It's quite nice to show it in reality and get them to watch a sort of a little video. And that little video is him playing football, and it's about prime numbers and stuff. And, yeah, quite awesome. Right. Have you ever done binomial expansion?
I've sat in a year 11 lesson when it was being done. That was last year. I've not touched it since then.
How did they teach it?
It was to do with Pascal's triangle.
Yeah.
That you'll never do up to, I think, 6 or 7, because after that it gets really conjected. It goes something along the lines of whatever level of Pascal's triangle it is, that is your coefficient of your n value, and it's raised to the power of n minus 1, I think it is.
That's very well remembered. Did they just tell the students, or did they get them to discover it somehow?
I can't remember. I mean, I came in on the second lesson. The first lesson was getting taught it. The second lesson was in practicing it.
I've seen this taught.
So it was a case of the teacher refreshed them.
Yeah. I've seen it taught in many different ways. It can be incredibly dry, because ultimately they are given the formula in the formula booklet, but if you rely on that, you know, they get to the exam, they have absolutely no idea. The formula looks incredibly complicated and they have no idea how to do it. So I really get them to avoid even bothering to look at the formula. They just learn how to do it themselves. And I've observed a lesson where they've done it using a sort of permutations and combinations method, where they've said, oh, you choose some of these and you choose some of those. So it's done from what seems like a completely random sort of way of starting, but actually we're just doing algebraic manipulation.
Yeah.
But actually it's all to do with coefficients. And I've tried that. I find it quite tricky, because I've kind of adapted someone else's lesson and I'm always struggling a little bit with it. But that's one way to do it. But the problem is the order, you know, because often this comes up quite early before you want to talk about those things. But often it's worth doing anyway, because they will eventually get the info. So the key thing about binomial, and I'm afraid that because it's on webinar I'm going to have to do it in quite boring way, is... Sorry, go on. Were you going to say something?
No. Talking to myself.
That's right. So binomial expansion. Basically, a binomial is just when you have two terms in a bracket. So a quadratic is a trinomial. Well, so it doesn't need to be necessarily in a bracket anyway. So this is a binomial. It's when we have one thing added to or taken away another thing, raised to a power, and we want to expand it. Do you have any idea why, apart from this fun algebra, this might be useful?
Uh, Not really, no.
No, no, and you know, why would you? And basically, before calculators, this was how you could work out things like this. So like 1.1 to the 5, what you could do is, it would only be an approximation, but a pretty good approximation. You could imagine that if this is 1 plus 0.1, what you
Yeah.
could do is you expand your brackets, you know, to the 5, and then
Mm.
with A and B, and then sub in A being 1 and B being 0.1, and that's a much easier way to calculate that. Well, actually, 1.1, I think probably, well, no, I think that probably is better. Either way, there's going to be quite a lot of time taken up. But that was basically how they could do these things without using a calculator. The way that I normally get students started on binomial expansion is obviously just to give them a load of different binomials and ask them to expand them. And then they get really bored and think that's really tedious. And they were like, oh, I wish there was a way to do this. Well, that's what you hope. You hope that one of them says that. And you go, well, what have you noticed about the coefficients? So I won't get you to bother doing all of these yourself, but if we expand x plus 1 squared, we get 1x squared plus 2x plus 1. So you get them doing all of this, and I think I've uploaded to the Student Central my worksheets that I used to give out, where that you get them so they're writing them down below each other as best as possible. But because they make loads of mistakes and stuff, I think on the back of the sheet, you then go, okay, now that you've actually worked it all out, write it down, each one. So x plus 1 cubed, you'd get, oh look, 1x cubed plus 3x squared plus 3x plus 1.
X cubed plus.
Yeah. Sorry,
That's what.
yeah.
14641.
Exactly. And then it's nice to include that one so that they can see that. And so you sort of, you do this, that you've written it up so you've got your ones there as well. And you say, oh, hang on, what do you notice about these coefficients? And at that point, a load of them have never seen Pascal's triangle, it turns out, which is weird because it's one of those things that I was definitely shown as a child at primary school. I have no idea why, except for maybe just for fun, wasn't it? Like, oh, look, you add these together, you get that one, you add this together, you get those. So this may be, for some of them, the first time they've ever seen Pascal's triangle. But fairly quickly, or even if they didn't know that was Pascal's triangle and you wrote this out, you could say, what do you notice? And hopefully they might notice that you add these two together, you get the next one. And thus you can always work out Pascal's triangle. So this is sort of the first half of the lesson, first lesson. Just getting to this Pascal's triangle bit. And discovered all of those. Oops. I'm jumping quite far ahead here, but you're right. I then get them to do 5 and 6 and maybe 7, just doing the adding them to get the next one. So they get the 1, 5, 10, 10, and 5, 1, and so on. Yeah. And then I sort of say to them, okay, now these are the coefficients, and this is where it starts to get tricky. So we go back to here and see, notice that these are the numbers in front. So what else do we notice about these things? And this is where we start to talk about the powers go down. And I write in sort of the x naughts here as well.
Yeah.
So it's just going back and unpicking it all and saying, look, here the powers go down, and the x naught, and here we've got the coefficients. Now I then bring in what's actually happening as well is this 1 is also being included. So we've got 1 to the 1, and the thing is that the 1s are there, but they're invisible. And then ultimately what's happening is this procedure. So there's a binomial sheet that I've uploaded, which is where you sort of point them to that they have to find the appropriate row of Pascal's triangle. So if this is x plus 1 to the, 6, then they need to go to the row 6, which starts 1, 6. It's the one that has the 6 as its second term in. Though you have to know that that actually has 7 terms. But they do find it a bit tricky because they go 1, 1, 1, 1, 2, 1. So if they're going to do that and put the 1 in, that is fine. But they have to remember that that one is row 0.
Yeah.
So yes, they have to. If they do that, they have to appreciate that they put it in a row 0. In that case.
Yeah, because anything power 0 is 1.
Yeah. And it's the same with this sort of first. So yes, this is the process. So they choose their row of Pascal's triangle, and I get them to just write their coefficients down with big gaps in between. So they've got their coefficients.
Yeah.
Then their first thing, their A, goes to the power of n, and it works its way down, going by 1 each time, and I get them to write that in, so like a to the 6, a to the 5, a to the 4, and get that written down. And then going the other way, the first term has no b in it, and they can go off the power of 1, or they just start writing from the other end, so they go b to the 6, b to the 5, b to the 4, put those all in. And that's basically, then they've written down their expansion, they then have to just work out each of the little bits. So, for example, to expand 2 plus 3x to the 5, we'd write down the row of Pascal's triangle. Obviously, they would generally write down the whole triangle. Sorry, I just wrote that there myself. But I think I tend to sort of go 1 plus 5. And it's good for them to put the pluses in front of their coefficient as well, because they have a tendency to forget what they're doing in terms of, when you expand things, you do this plus this one plus this one. They get a bit full of that. And then they've ended up like multiplying all of these numbers together, and it's just like one big mess and one big number. And I'm like, what on earth happened there? Then they take the A, and that starts with the highest power and works its way down. And they just need brackets to make sure that it doesn't look a complete mess. And I don't really need to put them both in the 2 to 0, but they can if they want. And then they do the same thing, working their way up from 0 if they want, or going from here and going backwards. It doesn't really matter, I suppose. Let's take it up to them. And how much space is there. And then they have to muddle through working all of those out. Now, generally, I think if they've done that first bit like this, they will probably get 2 marks in an exam. And then there'll be another 2 marks for sorting all of that out and getting it as correct as possible. So it's generally a 4-mark question. They might be given 3 marks just for doing those. They'll see coefficient, see all of those correct and all of those correct. And then 1 mark for the final thing. Depends how the marks come is. But there's often a lot of mistakes between this bit and the next bit. I'm not going to bother doing the next step, so I know I've got the answer. So when that's all messed around, that is what they get. And that would have been really tedious. I think one of the one of the major things is some of the students never fully engage with using the binomial expansion and still start expanding brackets. You know, they see the word expand and they will just be like 2 plus 3x times 2 plus 3x, and they work that out, and then they times on another 2 plus 3, and oh my goodness, what a mess. I've seen it done and I'm just like, oh my goodness, that must take you so long every time. But the idea is obviously to apply this method, which is much quicker at this first stage than multiplying everything out. And then it's just a case of doing this. Now, this always used to come up in the non-calculator paper, so that they had to do this. But from next year, there is not going to be a non-calculator paper, that because of the way that they are restructuring the A-level, it won't matter. So they'll get to be able to use their calculators, because that was the most tedious thing. It used to be 2 to the 5 you really had to know, and well, and even bigger numbers. Often they might not ask for the whole expansion, and instead they might just ask, what is the coefficient of the x to the 4 term? And it's a deliberate trap. They don't want the students to say 5, which is the Pascal's coefficient. They want them to have worked the whole thing out, not the whole thing, but this whole thing. And then the coefficient of that term is that number that's left once you've multiplied it all out. And that the students find quite tricky. They also find it quite tricky to identify that if they want the term x to the 4, that this is the bit they need to write down. They don't have to write all of this bit down. I think I'm getting ahead of myself. I think I should.
Yeah.
We'll probably have. Oh no, that's exactly what I'm saying. Students get confused between the binomial coefficients and the coefficients they get after expansion. So, well, in fact, the way that I've written that seems confusing. So the Pascal coefficients, they get confused between those, what they're talking about with those two. So to generate the coefficients without, this is just the Pascal coefficients first of all, without needing Pascal's triangle and having to go all the way, there is a formula. And this is the point at which you can do it in a way where they can do it actively using stuff that I sometimes speak for statistics, but it can be quite a nice way to do it now. And it's a sheet that I've uploaded called the binomial counter sheet. And it's just different color counters, and you say, I've got 3 counters. If I have 3, choose 2. What do I get? And they, from that, they can work out this formula. They don't need to know how the formula is generated, and it's given in the formula booklet, but they don't often know what it means. So it can be useful to sort of derive it with them. Anyway, the formula for the binomial expansion as a whole in the formula booklet is written like this. And so you can imagine why the students look at that. They have absolutely no idea. They could have been doing binomial expansion completely fine in class. And so it's a case of showing them both and saying that this is what it looks like in your formula booklet. You need to understand what this is. So this, the NC0, we say NCO though, NC1 for example, those are the Pascal triangle coefficients. To calculate them, it is n factorial over r factorial n minus r factorial. This is why I tend to do the little task that I've not really described, but basically the task is you give them these counters. So if you give them 4 different coloured counters, for example, a red, a yellow, blue and a green, and you say how many different ways can I arrange these, then hopefully they'll start doing that. And what they'll discover is that they can arrange them in 4 factorial ways. And so that will then introduce to them what factorial is. And then you can get them to choose. This is the number of ways that you can choose R things from a total of n things. So deriving the formula, I think it's worth it in order for them to be able to understand where it comes from. Because otherwise it's just a case of you just tell them, and you tell them what factorial means, and they can just do it. And if you were shorter time, that would be fine. So 20 choose 8. There is also a button on the calculator that just does that straight away anyway. And since it is now going to be completely calculator paper, they actually don't even really need to know this formula. So that will be interesting to see in the new A-level papers how they're going to test this, because the whole point was that people had to use the formula to calculate this because they didn't have calculators, whereas now they will, so they can just type it in. But either way, it's 20 factorial, so that's 20 times 19 times 18 times 17 and so on, over 8 factorial, 12 factorial. I get the students to, with these, to actually calculate them. I get them to write a few out. They'd need more than a few for this one. But you'd want to write them all down. I'm about to do this on the next page, and I've just jumped ahead again. But get them to write down quite a few, and then think about what cancels, because actually all the 12s will cancel with everything from 12 onwards. So everything from 12 onwards will be there, so it's already going. In fact, I think we need to do that. So on the top I'll only have that, and then on the bottom I'll have 8 times 7 times 6, and so on. And those will all be able to cancel in some way with the ones above. One. So that I can basically say, okay, well, 8 goes into 16, so that's twice. 7 goes into 14 twice. 6 goes into 18 3 times. 5 goes into, which one should I go for? 15 3 times. 4 goes to 20 4 times. 3, I just cancel those 3s. 2, I cancel those 2s. So my calculation that I now have for this is 19 times 17 times 5 times 3 times 2. It's still not brilliant. Oh, and a 13. Still not brilliant. But yes, from now on I have calculators, so it's less of a problem. So all of these coefficients can also be written like this. So this is another way that the formula is written. So that basically they put the formula in for each one. I think that's even less helpful and not something that the students at AS level need to think about at all. They just need to think, oh, I calculate my coefficient and apply the formula as I was doing it before the process. The benefit of this, though, is that at A2 level, they can use this one, and it's given in the formula booklet, for if n is not positive integer. So at AS level, they're only ever expected to expand things with a positive integer. As we can understand, I mean, in our brains, we understand what that means. That's something we've done. If we had a negative or a fraction, it becomes harder to understand, which is why it's then easier to think about it as a number. If you think this was 1 plus 0.1, so I've got 1.1 to a power, then it's easier to understand what it is to a negative power or a fraction. So then this formula can be used at A2, provided the x is tiny. So the x has to be between -1 and 1. That formula is only valid for that. And it is in fact an infinite series. So when we can expand something just to a positive integer, we get a finite series, don't we? It's finite expansion. And so if you were asked to expand that in an exam, they'd never be to more than 6 or 7 because it would take forever. However, if you're given a negative or fractional one, then you are going to find yourselves with an infinite series. but after about the fourth term, it's just so tiny that it doesn't matter. So whenever we're doing the full-on binomial expansion, it's only just an approximation, basically. So, is this for you to do? Yes, I want you to do this. So using what we've just talked about, binomial expansion, write down just the first 4 terms of this. That's a typical sort of exam question, so just get them to do 4 terms. So do you want me to write down the formula, in fact? For NCR?
Don't worry, I've written it down.
Oh, okay, cool. So yeah, use the formula for first 4 terms, which is a...
So I wasn't using the formula, I was just trying to do it the old-fashioned way.
What, using Pascal? You mean using Pascal? Oh, no.
Yeah, because I've already got Pascal's written down 1 to 10.
Oh, okay, fine. That'll be quicker for you then.
X to 9 plus 9x to the 8 plus 36x to the 7 plus... We should double check to make sure that's right.
Now, the key thing is, and I could tell just from what you were saying, yeah, there's 6x, yeah. But when you were saying it, did you say x to 9?
Oh, no, I was talking about the other numbers.
All right, sorry, I will not say that it.
No, I was looking at the 1 to the 9, 1 to the 8, 1 to the 7, cancelling them down, so it's reading it out loud.
Yeah, no, that's fine. Yeah, you're right. Yeah, good. Because it does, so when it says the first 4 terms, a lot of the students don't like, they don't know whether it means basically in ascending order or descending order, but because we tend to start with the 1 and work our way up, unless it says, then yes, always do that. So yes, should be 1 plus 9x plus 36x squared plus 84x cubed. Now, with a negative number, I tell the students just to make sure they put everything in a little bracket until they're ready to sort it all out. So have a go at doing that one. So say when you finish.
Yeah, will do. I think I've got it.
Okay, yeah.
I'm getting 1 take 21x plus 30x take 945x. Oh, sorry, that should be x squared take 945x cubed.
I got 189 for the second one. 7 choose 2, I got 21. And
yeah, sorry, I've done that wrong. Yeah, I've added 9 onto 21 instead of multiplying it. Yeah, 189.
Yeah, the thing is that between this layer and the next one, there's just so many potential mistakes, and the students, you know, you get a lot of doing -3 times something before squaring it and things like that. So it might be good to encourage students that need it to do an extra line in between, no matter how tedious that is, you know, so they've got sort of a 9x squared, and then so on. Sorry. But good, yeah. So as you can see, there are quite a lot of pitfalls, and it is very much sort of boils down to, you know, this sort of very attention-focused, detail-oriented algebra that isn't for everyone. I love doing it, but you know, a lot of the students are not keen. Now, the reason for doing it though is for things like this. So to find the value of 0.974, we can imagine that we could write that as 1 minus 0.03 to the 4. And we could write that as 1 minus x to the 4, expand all of that to get our expansion, and then sub x into here, which obviously seems absurd when they have calculators. But before calculators, that makes it a lot easier than it was. Now, what they get them to do sometimes is to do it to the 20, you know, something that's actually really big, and you just use the first 4 terms, and then you compare it to what it is on your calculator to see how accurate the approximation is. So this one says check on a calculator, but of course I just realised that I've done the full expansion there, so it should be exactly the same in this case. But normally if we do like something to the 20, and we only do the first 4 terms, you'd find that maybe it agrees up to 4 decimal places, for example. And that's the sort of question they might ask. Right, let's I know that was quite a whistle stop of binomial. And it's one of those things that when I first started teaching it, wow, I had to, like every year I had to really practice it to be able to remember the main bits of it, really. I don't know why, because I really get it now, but I don't know. I don't know, but it was one of those things that I just found tricky. Um, and, you know, it is one of the things that they find tricky too. So let's take a break. Any questions?
No, it's making sense now.
Yeah. It's a nice place to pick up marks. For those kids that are really procedural, they love it. But yes, there's a lot that you can do to make it more interesting to the other students too, which I haven't really been able to do with you today. But after the break, we will do sequences and series at an AS level. So 11 o'clock. Number 11 o'clock.
Yeah, happy with that.
Cool. Okay. See you then.
See you then.
actually in the kitchen.
Yeah.
I see you through the glass. That sun's shining like, oh, bloody hell. Tell you what, it's on me, don't I? It's bloody cold weather.
Oh, I know what you mean.
Bloody go. Right, black tie tonight.
Excellent.
Just a normal black tie. And we're going to pick Bill up at 5 o'clock. So we have to leave here about quarter.
Yeah, that's not a problem.
Right. Yeah, no problem. Is Brian still coming in here to
Yeah.
see you, Richie?
Yeah, 7:15.
Oh, it's all organised.
Yeah.
That's right. I was wondering about that.
Right, hi, say hi when you're back.
Sorry about that. My old neighbour popped over.
All right. I think we get any minute. I'm expecting a...
Literally.
Sorry?
Pardon?
I was just saying, I'm expecting a pastorer today, and I keep thinking he's going to turn up, and of course he probably won't turn up until just as I'm going out.
Yeah, always the way.
Yeah. Right, okay. So sequences and series is the rest of the webinar, and this is fairly involved at AS level. So what the students have done so far at GCSE and spent a really long time doing, obviously that knowledge is, you know, one thing as sort of part of it. So knowing the nth term, basically. And, you know, the idea of sort of having a sequence and having to look at the differences and all of that is not in AS at all. You know, it's gone beyond that because it's all about using formulae to find them. So there's quite a bit of notation that the students don't like, because I don't think, well, I don't know if any, I have a feeling this is now actually in GCSE using this sort of notation, but whether anyone actually does, who knows. So the sigma notation as well, again, is something that they might have been introduced to with GCSE, but not necessarily. So there's a lot of formulae in that thing. So, sorry, can you mute yourself? Oh, you don't need to mute yourself, it's only us. But the sort of nice way to start is to just, you know, leave them to it, give them a load of numbers and get them to start coming up with a sequence. And they can have absolutely any rule. So have a go, I don't know, pick some numbers and see if you can generate a sequence. And then tell me and justify to me what the pattern is. Or these numbers, sorry, to be more specific. So have you made a sequence from any of those numbers?
I'm just trying to find one that's decent and I can see one that jumps out, but
yeah,
it's not really...
Very interesting. Well, the students will obviously, there'll be lots of them that'll take the easiest one, and then there'll be lots like you who are searching for a really tricky one. And it's great because, from amongst the whole class, you're going to get loads. And there'll be loads that people have never would have come up with.
Yeah.
Yeah, then I have no idea what the 541 relates to. But I suppose if you get them to play around enough with all of them, they'll find a pattern that they do. Well, what jumped out at you initially?
Just the first three. So negative 0.1, 0.9. I was looking at that and thinking, how could you make a sequence out of that?
Okay.
Just play about with it.
Can you make a sequence out of those?
I'm not sure.
I don't think necessarily that you can with all of, I suppose it's whatever you define the sequence to be. If you're like, you add 0.1, then 0.9, then 0.1, then 0.9 each time, then yeah.
Yeah.
Or no, minus 0.1 to, no, 0.9. No. Oh yes, cool. So yeah, it is just the difference.
Yeah, I think I'm overcomplicating it.
Yeah. I think often the students will just start with like 4, 6, 8, just adding 2 each time. 6, 12, 18.
Yeah.
Adding 6 each time. They will tend to fall back on the adding something each time.
Yeah.
Although the 6, 12, 8, they might sort of say they're not adding 6 each time, and that is actually an nth term of the sort of, a 3 times table or a 6 times table. So that is in fact 6n. What else am I looking at? 1, 3, 12, you could say you times by 3, then you times by 4, the next one could be you times by 5, the next 6, that sort of thing. There must be something to do with that. That's the difference. So, oh yes, I know. It's Fibonacci. It's not the Fibonacci sequence, sorry, but it's the ones where you add the 2 previous to get the next. So minus 0.1 plus 1 is 0.9. So your next one would be 1.9. And then your next one would be 2.8. So, yeah. That's quite a nice one. So, adding the previous 2 to get the next. Multiplying things. The weird using the difference to get the next one. Anyway, you'll see that they'll come up with all sorts of things. But I think in general they tend to fall back on the things where you just add things together. Now, there are 2 ways that we define series. The students do know this already because these are the ways that they previously did things. You give them, I think, possibly, I would normally actually say this one first, because if you have a series or sequence, for example, very simple series where we just add 2, and you say, what is the next one in the sequence? Then they're going to go, oh, I'm adding 2 each time, so the next one's 9. So that's the inductive definition is you add 2 to the previous one. And you can only get the next term from the previous ones. So an inductive definition of a series can be very tight, and it's not particularly helpful if you want to know the 200 one, because you're going to have to keep going. And the way that we write the inductive definition is we use this terminology, and the students really hate it. They just don't seem to understand why we do this. I think if they had it their way, they'd just be like, the next one n equals the last one plus 2, So we use the n+1. So U, it doesn't have to be U, it could be an A, a K, it could be any letter. But we have the subscript n+1. So the next term is the general term, the previous term, plus 3, for example. And as I said, so un+1 is the value of the next term in the series. Un is the value of the current term. So then u1 equals 5 is important to know because we have to know the first one in order to get the next one. So in terms of the sequences that I was talking about before, the one where you add the, if you add minus 0.1 plus 0.9, what would that be? That would be to get the next, so you'd have to do it like this, I think. To get the previous ones, to get un+2, oops, no, it's not plus, you have to add the two previous terms. So that would be an inductive definition. The deductive definition, that is where you can deduce any number in the sequence. So if you want to find the 200, that's fine because we have come up with a definition which is related to its position in the series, and that's what the nth term is. So we still write it like this with the un, that means the nth term is just the value of any term. That's what an nth term is, the value of any term. And n is its position, as it is here. But we then have a formula related to the position. So the n gives you the position in the series. So to get the fifth term, we do 5 times 3 plus 1. So the fifth term, and that should say, so U5 is 16. So from GCSE, the students do know these things, they just don't know that they're called the deductive and inductive, and haven't seen them as like this. Normally they just say nth term, don't they? They don't necessarily write U subscript n, and they won't really have seen that either. They will just say add 3 to the next one to get the next one. Have you seen this before? Have you done AS level sequencing theories at all?
I think a bit of it at college, but a bit out of practice.
Yeah, and there's quite a lot of bits to it. I would say it's quite a bitty topic. And basically you can spend, there are so many resources to do sequencing theories. You can spend so much time just getting them to play around and discover lots of things. And I guess really it's all just about time and whether it's necessary. I think it's a tricky one with sequencing theories because I think it's fairly straightforward. But for the students that don't like learning formulae off the heart, perhaps it's not. So these are just sort of ways that they can get used to this feeling of how things behave and what's happening. So if you plug in the first 5, find the first 5 terms and 10, 100, 500, 1,000 of these and have a look at what's happening. So you have to do all the 10, 100, 500,000 if you know what's happening.
Right, I've done the first 5 terms for each of them.
Yep. What do you notice?
Do you want me to go and do the 10th, 100th, 500th and 1000th?
Maybe just do the 100 for the B and C, if it helps. I mean, you
Okay.
might. Well, no. Well, you might already be able to spot what's happening anyway. What have you noticed? What with A, for example, what's happening?
With A, it's basically, you've got 3 and you're adding on, well, n take 1, amount of zeros, and then a 1. So for the 100th, it'll be a 3.99 zeros, then 1. For the thousands, it'll be 3.999 zeros, then a 1.
Yeah. So it's getting...
For B, I left it as fractions. For C, I left it as fractions.
Okay. So what, in terms of tending towards something, for A, you start with 3 and the 10th, and it gets smaller and smaller and smaller, the little amount that you're adding on. So effectively, we say that it tends towards 3. The limit of the series is 3. What did you notice about B? Did it look like it was tending towards the limit? Or not?
Yes, it's getting smaller and smaller.
Yeah. I think we would probably say that it was converging towards 0, because sort of like the 100 one is 0.0000999. So yeah, the limit there is tending towards a 0, I think. But what about C?
I'm just going to work out the fractions.
Mm-hmm.
I'd say the same with C, it's tending towards 0.
Oh, I've got it going the other way.
What
As in, so I got 3 over 2 and then 9 over 6.
I've got something in wrong then in my calculation, because I got 9/10 from a second. I got 3 over 2 from a first.
Hold on.
Just plug that back in.
Oh, because 2 squared is 4 plus 2 is 6.
Divided by 2 cubed plus 2.
I got C1 and C2 to both be 1.5.
Yeah, for C I'm still getting for the second term 9 over 10.
So because of the bottom here, and so
Yeah,
2
so I'm
squared is 4.
doing cubed rather than squared.
Okay, right. Okay, so that's interesting. So that
Yeah,
must
I
make
was
the
doing
difference.
a cubed instead of squared.
Yeah, and that must make all the difference. So then, with that cubed, and that's like the first one here,
Yeah.
it converges towards 0. But when that's a squared, what actually happened was I got 1.5, 1.5, 1.58, 1.65, 1.7, 1.98 is 100. So it is, in fact, diverging. It doesn't have a limit. Well, I mean, it could do, but I don't think so. I think it's just diverging very, very slowly towards infinity. So yeah, so that the idea of this was just to get them playing around and see that the more that you add, sometimes it makes really very little difference, and so you actually end up getting closer and closer to this. And so there are different ways that we describe series. So we say a sequence is convergent if it gets closer and closer to a particular value. So those first two were both convergent, and the limit was 3 in the first case and 0 in the other one. The third one is divergent because it doesn't converge towards the limit. Infinity does not count as a limit. We call a sequence periodic if it has a repeated pattern. So in fact, you know, the prime numbers, the perfect square thing we were looking at earlier, that would be a periodic sequence because it goes, I can't remember, it goes 1, 4, 9, 6, you know, the ending bits, and then it goes round again doing the same ones. The period is the number of terms before it repeats itself. So if it's going 136, 136, 136, then the period is 3, for example. And a sequence is oscillating if it's going up and down, above and below a middle value. It can be both periodic and oscillating because it can just keep stepping down and doing the same pattern over and over again, but not necessarily. So for this one, what we're going to do is look at various sequences where, actually I'm just looking at the time thinking actually we don't really have time for this, we'll just move on actually. But I've got many things that I've uploaded, that all sorts of things where they play around and investigate what's happening with different sequences. But I think I'm going to move on a bit so we can get on with it. So here is one where a sequence is defined deductively. So that's basically an nth term that we've been given there as AK, so that's the nth term bit, is 3 times the k, wherever the position is, minus 1. So write down the first 6 terms and evaluate this. Do you know what this means?
K is the starting value, sorry, K equals 1 is the starting value, K equals 6 is the top, so it's terms 1, 2, 3, 4, 5, 6.
Good, yeah. And it's the sum of them. Yeah, so sigma.
Oh, yeah.
Yeah, the sum of them. And that actually is a key distinction that the students forget. They do forget to do them. So really, part 1 leads directly to part 2 in this case. So just quickly calculate the first 6 terms of the sequence and then add them together.
Got it.
Yeah, what have you got?
2, 5, 8, 11, 14, 17.
Yeah.
And the sum of AK 1 to 6 as 57.
Good. Yeah. Excellent. So it takes students a lot longer to get used to this notation. And here it's quite simple because it says k equals 1 to k equals 6, so it's starting from the first term. They get a bit confused when it doesn't necessarily start at 1, and then say it's going from 2 to 6. They get confused about whether they need to go up to the 6th term or whether they need 6 terms. But yeah, that as it's quite clear, k equals, and hopefully it should be quite clear. So here's another one. I'll have a go at doing the same sort of thing. I think part 3, to say, describe the behaviour of the sequence, really.
I think I've got it.
Yep. What have you got?
I'm just not too sure about the description of the pattern. I think I might have gone wrong here.
Okay.
But for part I, I've got it's oscillating about 0 plus or minus 1.
Yeah, yeah.
And evaluation of the sum of k equals 2 to 5 as 0. And the sequence defined by bk equals 5 plus negative 1 to the power of k times 2 as oscillating plus or 2 about 5. Or
Yeah.
plus or minus 2 about 5.
Yes. So they are oscillating, definitely. But you could also say they're periodic, because of course it does repeat. But your part 2,
Yeah.
because it's going from 2 to 5, it's left off the first one. So actually you end up with 1. Because you've got, you haven't got that one. So you've just got 1 plus minus 1 plus 1 plus minus 1 plus 1, which ends up with a 1. There we go. Oh no, 0. From k to 2. Oh, sorry. 1
Yeah,
is
'cause
0.
you've got 4.
Yes, sorry. That was 6 of them. I just assumed that
Yeah, because only 4
sorry.
terms.
Fell straight into my own trap. Yes, 0 is correct. The other thing is, actually about this is a geometric sequence, which we're going to talk about in a minute, where the common ratio, we're multiplying by minus 1 each time, because that's the nature of it, isn't it? It's just something to a power. So each time we just increase the power, we just multiply by minus 1 again. So it is a geometric sequence with common ratio minus 1. And yes, oscillating and periodic. And yeah, you can either write it out and say it's oscillating periodic to a period of 2, but you're right, it is oscillating either side of 5, which is quite clear from sort of looking at it. Good. These are the things that I've uploaded just to show you the names of the sources. And, you know, this again would be fine if we were actually face-to-face and actually had needed quite a load of people to do a bit more fun. But it's just a case of, you know, getting them to generate an nth term and getting the other one to do it. Quite a nice one is the odd ones out, because it's getting their brains to do that sort of scanning, the quick scanning of, oh, let's think, running through lots of trial and error, which is something like something that they just don't seem to really necessarily possess, or they forget, or they just think that that is too much like hard work and they can't be bothered. Hopefully this will get them going, oh, I could do 2 times 4, 8 times 4 is 32, so the 18, that could be the odd one out. Oh, I'm adding 3 in the next one. And in fact, nothing's odd one out. Might be the odd one out in none of the other. Oh, right, or in fact, it could just be the odd one out between not just the different numbers, but the different series. Anyway, it's just one, again, it's something for them to look at and try. Now we're going to look at the 2 main types of sequences that occur at AS level. Those are arithmetic, which is a very typical sequence where you just add on the same difference. Can you write down the inductive and deductive definitions for this sequence? So remember, the inductive one is when you describe it in terms of the previous one, and the deductive is the nth term, so using a position. So what are you looking down for each one? So have you figured out your nth term?
I'm looking at it now.
Right. Okay.
Yeah, I can't really figure these out. I'm getting confused with myself.
So going back to G sub E, we look at the differences between them. And we're adding on 5.
Yeah, I've got that.
Yep. So it must be something to do with, if we do that, then we know it must be something to do with 5n. So 5n would be 5, 50.
Oh yes, it's 5 and take 2.
Yeah, because what we then do, you can either just go back one and find that one, and then that is your nth term, 5n minus 2, or you can just look between the 5 and the 6. So yeah, so the deductive definition, the nth term is un equals 5n minus 2. So yeah, so the deductive is un is 5n minus 2. And the inductive is un plus 1 is what? How do I describe the what's happening?
Just n plus 5.
Oh, well, we write it as the previous term, which is our un plus 5. Yeah.
Oh yeah.
Yeah, so that is the difference. But you're right, that's what the students want to do. They want to write an n. So we only put the n in, that refers to the position. Otherwise, if we're talking about the term, it is a un or an ak or something with a superscript, basically. But that is something that, if you were teaching this before we got to where we are now, we'd do a lot of practice of those two things. But if we look at what's happening and just write our terms out in terms of our subscript, so u1 is 3, u2 is 3 plus 5, u3 is 3 plus 2 lots of 5, and then u4 is going to be the 3 plus the 5 lots of 5. What we can actually do is take our inductive definition and see that we are in fact making a pattern. So if we generalize this, we can say, okay, let's call the first term A, that's our 3, and the difference between them, the 5, is called the common difference, and we'll call that D. Then I can replace my 3's and 5's with those. So I end up that U1, oh, and this is called an arithmetic sequence because we're adding on the same each time. So U1 is A, so U2 is just my A plus D, U3 is my A plus 2D, U4 is A plus 3D, so UN will be A plus N minus 1D. So that means for any arithmetic sequence, this is true. Anytime you are adding on the same amount, just a common difference, the way to calculate the nth term is to use this formula. So if we do that now, So this is why we no longer have to do the methods of differences. And I do this with the kids because they totally have forgotten how to do this. They sort of struggle, to come up with the 5n minus 2. And so you say, well, don't worry, there's now this formula that's given in the formula booklet, and you just have to be able to sub stuff into it. So the A is the first term. The n minus 1 is the bit that stays there because that's going to give you the n. And your difference is 5. So if I multiply that all out, I get 3 plus 5n minus 5, which is 5n minus 2. So that is the nth term for any arithmetic sequence. So any time you're adding them in, that's what you get. So then, from then, the students never ever have to know they have to do this method of differences or anything. They can just simply use this calculation. So many of them don't, though. They prefer to go back to what they know and do it like this, which is all very well, but they also do need to know this formula in case they're not given the first few terms and they've got more complicated things to do. Now, when we have just the numbers written out like this, that's when it's called a sequence. When we start writing plus signs in between them, that's known as a series. It's a slightly odd distinction, but basically if I write it like this is what a series is. And if you want the sum of a series, what you're asking for is the sum of a particular number of terms in a series. So for example here, they've said consider 1 plus 2 plus 3, all the numbers up to 100. So we're summing a series, an arithmetic series. Now, the common difference is just 1, and your first term is 1. So we know from that we can find any nth term, but we know all our terms. We just need to find them and add them up. We want a quick way to do this. Now, there is a quick way, luckily. This is just what I was saying. It's called an arithmetic series or an arithmetic progression, and it's just our sequence written like this. So let's imagine, going back to this one, that we want to know the total sum of the first 20 terms. Rather than having to work them all out and add them together, there is a quicker way to do it. So if we imagine we have worked some of them out, let's just say that we've worked out the 20 and we were going to add them together. In reverse order, it would look like this. And the reason I'm doing that is that if I then added the two of those together, what happens is when each of those add up, I'll get the same number all the way along because of the way that it works. So, because this is just a mirror image of that. So we're going to get 101, and we've got 20 of those. So we've got 20 lots of 101. So that means that I can easily say, well, that was 2 lots of the sum. I just want 1 lot of them, so I just need to halve it. So 20 times 101 divided by 2 is 1010. So the sum of the first 20 terms of this series is 1010. And that was much quicker than having to work them all out and add them together. And in fact, we can do that exact same thing going back to this one. We could again write them all out all the way up to 100 and then do it in reverse. And in fact, this is going to be exactly the same, isn't it? Exactly the same, except that I've got a different number of terms. So I haven't this time got 20 of them. I've got 100 of them. So the sum of the first 100 numbers, I'm going to have 100 lots of 101. And then I divide that by 2. So the sum of the first 100 numbers, sorry, I can't pull this words out of my head, whereas I should be able to. 50-50, yeah. Is 5,050. That's the first 100. And we can generalize this into algebra as well. So if we now think about what we were doing in terms of our A and D, for each of our nth terms, we know the first term is called A, so the second term is just A plus our common difference, the third term is A plus 2 lots of our common difference, and so on, all the way up to the nth term, where it's A plus the previous ones before times D. Again, we write that in reverse order. And what happens when we add these two together, we'll get 2 A's plus n minus 1 D. And that's the same for all of those. Now, we've got n of those, because that's what the sum that we're doing. So we've got n lots of 2a plus n minus 1d. To get our sum of the n terms, we just need to divide by 2. And so the general formula for finding the sum of a series is n over 2, or half n, of 2a plus n minus 1d. It's a really nice one to show. It's not something that they need to know, but it's quite nice to show them, especially with the numbers, so that they could then add up, any number of numbers that they wanted. And again, this is also given in the formula booklet, but that is the sum of the series of an arithmetic series. So here are the formulas. Because a plus n minus 1d is actually the last term, they do sometimes call that L, and they can just say, if you add the first and the last term together, times it by the number that you've got, the number of terms, and divide by 2, that achieves exactly the same. You know, like when we were adding from 1 to 100, because of the way that we reverse it, we do the 1 plus 100, 9 times 2, and so on. It's the same as just doing 1 times 1 plus 100. So if we'd been asked to add up all the numbers from 1 to 200, that's great. We just do 1 plus 200, and then times 200 divided by 2. If you are told the first and the last, you need to know the difference, the number of terms. You just take them away from each other, divide by how many are, and you're always going to catch out by the fact that you have an extra 1. But that's not something, that's something you can generally work out. So that was quite a lot of stuff, but now can you use them to work out the 17th term in this sequence? So identify what your A is your first term, D is your common difference, and then your nth term is A plus n minus 1D.
Is U17 negative 36?
Yeah. Yeah. Good. Yeah. That's right.
It's all fallen into place now.
Yeah.
Come back to me.
I mean, it's one of those things that there's lots of little bits to it. So how many terms are there in the sequence? That's the one I put before, which was it's the last minus the first divided by the difference, and then you add 1.
Is it 159?
Yeah. And I think I don't bother remembering that. What I tend to do is actually just use the formula and fill in what I know and then just use it to, obviously if I just rearrange that, then I'll get in. So that you only need to know this.
Yeah, that's what I just did.
Yeah, absolutely.
Multiplied out the brackets.
Yeah.
Worked out 4n is 36, yeah. Divided it.
Yeah. Good. Right, so this is a bit mean because it's not telling you exactly what term that is, but it wants to know what the sum of this is. We're going to have to do that same thing again and then use the sum. Actually, you don't necessarily need to work out what that one is, actually, because you've got the first and the last. You can work out the sum. You can just do n over 2 equals L, actually. No, we don't know what n is. I'm really sorry, you can't just do that one.
Is question 3 negative 126?
Hang on. Oh, I've got negative 2.2. Let me press it.
So I can't hear you. Volume's just dropped for some strange reason.
Oh, sorry. I was just saying I've got minus 252, but let me just see. I might have done it wrong. No, I've got minus 252.
Yeah, you got it right up. I see what I did wrong.
Is yours half of mine? No.
Yeah, I did half times 10.5 because I've halved it in my head.
In your head, yeah.
In the calculator.
Yeah. Half which one?
I knew it was half of n, and I knew n was 21, but didn't realise I already put in 0.5 times in my calculator.
Yeah.
Oops.
Now find the sum of the first 100 terms of that sequence. Have you just got a number that seems ridiculously large? But I think it is, Kate, it is true.
Yeah, 1337.5.
Yeah. I know it seems absurd, doesn't it, that 100 of those little numbers, even increasing by only 0.25, could be so big, but that is it. Yeah. I think it's quite difficult with sequences and series to tell the order of magnitude necessarily, because of the scope of how large that gets is kind of. Just to show you this is the sort of question they love to give because it involves a lot of different things. A fifth term of 21 and a 17th term of 69. Find the first term of common difference. It's just simultaneous equations. So the fifth term, we know that we could write that as a plus 4d, and that's 21. And the 17th term is a plus 16d, and that's 69. So taking those away from each other, we've just got the 12d is 48, so d is 4. Pop that back in, and a is 5. The students already by AS level have completely forgotten how to do simultaneous equations, but hopefully with a bit of a reminder, they'll get used to this sort of question. So they like to do that because it proves that you know the formulae. Just quickly, because we're sort of running out of time now, but geometric sequences, where arithmetic sequences we're adding on a common difference, a geometric one is when we're multiplying by a constant. And we call that a common ratio, which we tend to call R. So for example here, 2 times 3 times 3 times 3, R is 3. Again, inductive definition is just going to be what the previous is 3 times the, no, the next one is 3 times the previous. So u n plus 1 is going to be 3 times un. The deductive, now this is where for nth terms, the students aren't used to coming up with nth terms for geometric sequences. The ones with the ratio, with the differences that they did at GCSE, they were all arithmetic sequences. So they'll sort of try their differences and be like, or, you know, so that's not working for them. They could easily spot it, I suppose, but it's a bit trickier. Anyway, luckily, just as before, if we write down what's happening, we've got just 2. 6 is 2 times 3, so we use our inductive one. The third one is 2 times 3 squared, and so on, so that we can see that it's actually going to be our 2 times 3 to the n minus 1. So that's just a times r to the n minus 1. So that is our nth term for a geometric sequence. It's very easy to forget and think that it's AR to the n, but luckily it is given in the formula booklet at the moment. So they just need to practice it and get used to using it. We won't do this, we'll move on. But again, when we sum a sequence, we get a series. And the sum of the geometric series, again, has a sort of a way to determine the formula. If we think about each of our terms, they're A, AR, AR squared, AR cubed, up to AR to the n minus 1. So that our sum of n is just adding each of those. Now here's the trick. So the trick with the arithmetic one is to know you write it in reverse and add them together. Here, the trick is that you multiply by r. So when we multiply by r, we get AR plus AR squared and so on. If we now do our original one and take away this one, or the other way around, it doesn't matter which way you do it, you'll notice though that these will all cancel out. AR squared, all the way up to AR to the n. So you get the A left here and the AR to the n. And on the other side you've done Sn minus R Sn. So if we factorise the S of n, and we can factorize the A if we want. And then divide by the 1 minus r, we get our formula. So by doing Sn minus Rsn, we get this first formula. If we'd done it the other way around and Rsn first, we'd get this second formula. It doesn't matter, they're both usable. We tend to use the first one if R is smaller than 1, and we tend to use this one if R is bigger than 1, just to avoid getting a negative on the bottom. But anyway, those are the formulae, it's the same formula, for the sum of a geometric series. Now, the only additional thing that a geometric series has is the sum to infinity. And we can do that if it's a convergent series. So the first one you can see is divergent. The second one is converging. And that means that because it heads towards a particular limit, we can find the sum to infinity, because effectively it sort of gets to that limit, and everything else as you're adding near the limit is so tiny that it doesn't matter. So you can effectively add up all the ones that were on the way to getting there. Now the key difference between these is that 5 times 3 times 3 times 3 times 3, you've got a positive larger than 1 common ratio. Here we've got 40 divided by 2, which is multiplying by a half. So because our common ratio is a half, so it's less than 1, we can work out the sum to infinity. So a geometric series converges when its common ratio is between -1 and 1. When that happens, this r to the n is so small, because this is basically a fraction, it gets smaller and smaller and smaller, so this bit disappears, and we're just left with a over 1 minus r. So to calculate our sum to infinity, for this one, 40 plus 20 plus 10 plus 5. 40 is our first term, our common ratio is a half, so 1 minus half is a half, 40 divided by half is 80. So if we were to add up all the terms, it would basically approximate to 80. And it's crazy, isn't it? Because it's 40, 60, 70, it's already at 75, but it's going to continue to get so small that all those tiny little bits still only mean that it's 80. Now, if I know that the sum to infinity is 5 and a is 3, can you find the common ratio? So just put it into the formula. Here, and work out the common ratio.
Is it 0.4?
Yeah. And as you can imagine, the students find this really difficult because they find rearranging formulae and solving equations that involve that really difficult. So I get all sorts of things involving 2/3 and stuff because they've kind of taken the A over, just like left this 1 minus r floating there, and all sorts. So yeah, that's really difficult. So here are just the formulae for those things. So the geometric series just includes the sum to infinity. And then we've got some examples for your sort of running. well, we will do, so find the 7th term. I'll write this down. So it's just AR to the n minus 1. So find the 7th term for that series.
Quite a large number.
Yeah, I know. Is it 5832?
191,102,976.
Oh, no, that really is a large number. My height, I've just got 5832 because my R is just 3. 8 times 3 times 3 times 3. So I've got 3, and n minus 1 is 6.
I know what I did wrong.
We use the common difference.
Yeah, I did the AR then to the power rather than the index first. I forgot bed mass.
Okay, yeah. Yeah, that's easily done, isn't it? So hopefully...
Yeah, I got cocky and did 3 times 8 then to the power of 6 rather than
well,
3 to the power of 6 times 8.
At least you realise that you did have quite a ridiculously large number. That really is quite large. Also, with the 7th, obviously, it's only if you want, you could easily check it. Okay, so this one I'm just going to show you. Again, we set up simultaneous equations for this one because they want to know A and R. The students are definitely not used to doing simultaneous equations that don't involve just adding. So we've got AR squared is 12 and AR to the 5 is minus 96. They don't realise that they can do, I mean, they can rearrange it and substitute it, but that's just unwieldy, really. Whereas if you do the second one divided by the first one, you get, I might write this down. So I've got...
R to 3 equals negative 8?
Yes. 8, yeah, exactly. So I advise, first of all, showing them that you do this one in between, to show them how to do the cancelling of indices and what you're doing, basically. Yeah, so R is
-2.
Yeah, and then pop that back in, and A is 3. Yeah. But the first time I show them that, they really are just, I don't think they would have got that necessarily by themselves. They'd have tried to rearrange one of them and pop it into the other, and that would work fine, provided they did the A, otherwise they did so let's jump 3 and just do 4. Oh no, that's the, oh yeah, some of the terms of the infinite sequence. Yes. Yeah, let's just do this one. Oh, well, no, they're both different. You see, this is the problem with geometry. We've got 2 different things. Well, let's do them both. I think that's the end of that. Oops. Oh, I'll give you that. There you go. N equals 10. Okay. Anyway, have a go at doing it now that you've got AR and N and 10. Let me do the formula. So the formula for the sum is A1 minus R to the N over 1 minus R. Or, because R is bigger than 1, it's probably better to do R to the N minus 1 over R minus 1.
Question 4, 2/9 or 0.2 recurrent?
Quite possibly. 2 divided by 1 minus R. Yes, it is, yeah.
That was kind of easy to spot because you can see it's adding up a divisor of 10.
Yeah.
So 0.02, so 0.2 plus 0.02, etc., etc. It's going to be 0.2 recurring if it's infinite.
Yeah. And in fact, so just putting it into here, so 0.2 divided by 1 minus a tenth, so 9 tenths, 0.9, 0.2.
Yeah.
Yeah. And then this one here, have you done that one? I haven't done it yet. I've got some enormous number for that as well. Oh, but it has an enormous number there, so it's not much. Can you grab my iPad? Because I emailed Liz. I'm just going to see whether she's emailed me back. Oh. Right, Liz has just said, what's your number? I can call. I should have got her to, I should have looked at it earlier. She might call in the next 2 seconds. Otherwise, listen. Sorry, well, have you done that?
I made a mistake. I've just realised, so I'll need a moment's view. I'm getting 488,281.2.
Yeah, good.
Excellent. Yep, I realised what I did wrong and rectified it.
But that's the key thing, I think, with these. It isn't anything particularly difficult. It is just number crunching. And so, there's just so much room for error. But that is it. We've reached the end. I'm sorry that I didn't... Oh, there we go. That might be Liz. There we go. Hi, Liz. I'm good, thank you. Yeah.
might be that, and they can be currently as well, and they might want to add, you know, if say for example, if it's a reflection and they want to add some examples of work that, or if it's a lesson plan, then they also want to add their observation feedback, you know, something like that. And then what we're suggesting is that they write a 200-word reflection on, you know, basically responding to the criteria that is given.
So for each of those three?
Sorry?
For each of those three?
For each of the three. And then
Yeah.
what they do is, I'm sort of going to not very much time on that, because you're not really going to be looking at it for like four.
Okay.
That's something that they have to do. But I'm not telling them quite that. But I'm just saying, you know, don't spend much of your time on this. Just get that in, get that done, so at least you define them. The main thing is that then you expect one of those pieces to develop that, and that's where your critical analysis.
Good. Okay, that was the impression that we got. That was good. Okay.
Right. So yeah, so that's exactly. Unfortunately, both the experts
and to show the breadth. It shows the breadth as well.
Yeah, exactly. So I mean, it's a bit tick box to that first thing, and really when we come to market, we're going to have to take it.
Okay. Yeah.
In a sense, you're not going to mark them on that first thing, but if they're not there, we can't just mark them all.
Okay. Excellent.
Yeah.
Okay, thanks for confirming. That's brilliant. I just quickly ask you as well, sorry, for cohort 4's assignment, did we decide who's going to be moderating that? Oh, cool. Okay.
We talked about that. My colleague, we did
right.
So it's just going to email you, and it wants to moderate. So it's not and moderate.
Oh, it doesn't matter. Whenever he sends it over.
I think it's what they're going to do is that the course managers do
okay. Brilliant. Okay. Oh, well, that's fine. I'll wait until I get an email and see. That's fine. Brilliant. Okay. Thanks very much. That's great. Yes. Did you see the email that I sent about Robert a while ago? I think he was just feeling little unsupported by his not in his school by his mentor, but just from the sort of university point of view in terms of I don't know, is it Bristol or Bath? I can't remember who goes down to see him. They were planning on organising someone to go see him, and he felt that the guy who came to see him just wasn't very helpful. I think I emailed you about it. To be honest, he seems a bit bogged down at the moment, so he's a bit behind things at the moment, but he's just focusing on doing it. Well, he did this assignment. His assignment is good. Okay. It's okay. Yeah. Yeah, just see how he's going. Okay, cheers. Yeah, very good, and his essay was excellent.
Very nitty, isn't it?
Yes, very. Yeah. Yeah, see you there. Oh, I hope we're going to receive some more information soon, are we, about that? Great. Okay, fantastic. Thank you. Cheers, bye. Sorry that I got a bit sort of like, there you go, I don't get to talk to Liz very much, got into other things. Did you hear what she said?
It's all right.
Did you hear what she said?
No, I didn't.
Sorry, I was trying to put it on the speakerphone, but then realised that I was holding the phone the wrong way around. What she was saying was the 3 excerpts basically add make sure there's like a 200-word reflection on each of those.
Okay.
And submit them, and possibly add in a lesson observation that went with it, or an example of students' work. But don't spend. But she said, but don't spend too much time on that. it's kind of more of a tick box requirement a bit. The main thing that will be marked for critical analysis and evaluation and all of that is the poster. So you're going to take your one excerpt that is your favourite, or the only one that you can find theory on, whichever it is, and take that and do all the theory and the critical analysis and the evaluation, demonstration of progress, all of that, and do it on the poster. So that the poster is the bit that I'm going to be marking really for the critical side. So that's great. That's the first option that we thought. You don't have to do all three to a great detail, just one of them.
Excellent.
Good. Okay. Well, I'll send you the recording of